Okay, in this vodcast, what we're going to do is, again, continue our discussion of bonding. And what we're going to talk about now are intermolecular forces. So up until this point, what we've been talking about are intramolecular forces. In other words, when we talk about the strength of the bond between the sodium ion and the chloride ion in the lattice structure, sodium chloride, that's an intramolecular force. Probably should have drawn this over here. So what you're talking about is the strength of the bond between the positive ion sodium and the negative ion chloride. Intermolecular forces are when we have interactions between molecules. So, for example, back here to the intramolecular, you've got the positive ion and the negative ion. The bond that holds those two things together is an intramolecular force. If you were talking about a covalent compound, say carbon dioxide, double bond, lone pairs, the intramolecular force is the strength of the bond between the carbon and the oxygen, or for that matter, the carbon and this oxygen. When we talk about intermolecular forces, what that means is, let's say you have a water molecule and you have another water molecule next to it. It's the interaction between this molecule and that molecule. So intermolecular forces are between adjoining separate molecules. Intramolecular is the bond within the molecule or compound itself. What we're going to do is talk about various intermolecular forces and what their effect on properties of the compounds are. So the first intermolecular force that we're going to talk about is called hydrogen bonding. Okay, in hydrogen bonding, what you're talking about is the interaction. In fact, here, let me draw an ammonia structure, and let's put another ammonia structure here. So when we talk about hydrogen bonding, it's an intermolecular force. So we're talking about the attraction between this molecule of ammonia and this molecule of ammonia. So for hydrogen bonding to take place, the compound itself has to contain hydrogen, but then it also has to contain one of these three elements, either nitrogen, oxygen, or fluorine. So ammonia, you can see, obviously contains hydrogen, and it also contains nitrogen. So ammonia can undergo hydrogen bonding. What happens in this case with hydrogen bonding is the positive side of the molecule, and we're going to say it's the hydrogen for right now, and the negative side of an adjoining molecule, it's those two electrons. There's an interaction between that positive side and that negative side, holding those two molecules near one another. Now you've got to remember that that's not a bond like the bond between nitrogen and hydrogen. It's an interaction between this ammonia molecule and that ammonia molecule. For example, water will do the same thing. You've got hydrogen, oxygen, and hydrogen, two lone pairs, hydrogen, oxygen, hydrogen, two lone pairs. It's that interaction between the negative side and the positive side. So let's talk about what makes this side of the molecule negative and what side and that side of the molecule positive. If you think back to our discussion about electronegativity differences, you'll notice that oxygen has a greater electronegativity than hydrogen. So if we're looking at a water molecule, and I'm going to draw another one here. So if you're looking at a water molecule, you've got hydrogen, oxygen, and hydrogen. And they're going to share a pair of electrons here, and they're going to share a pair of electrons here. Well, if you remember back to our discussion about electronegativity, oxygen has a greater electronegativity, so it's going to hold those electrons closer to it. Now again, remember, these are still being held together by those overlapping orbitals, but since the electrons are closer to the oxygen, that oxygen side is going to have a partial negative charge. And a lowercase delta with a negative means that side of the molecule is partially negative. The other thing that makes it partially negative is the two lone pairs of electrons that are present. So if you were drawing this, hydrogen, oxygen, hydrogen, we say that side of the molecule is partially negative. Now since those electrons are further away from the hydrogen, we say that side is partially positive. So what you're looking at here is a difference in where the concentration of electrons are. Wherever the concentration of electrons is tells you the side of the molecule that is partially negative. So what this leads to is whether a bond is polar or nonpolar. So for example, let's take a look at our water molecule again. You've got hydrogen, oxygen, hydrogen. We said that this side of the molecule is partially negative and that side is partially positive. So where there is an uneven distribution of electrons to make one side negative and one side positive, we say that that molecule is polar. On the other hand, let's say we're talking about the compound H2. And you've got hydrogen and hydrogen. Their electronegativity differences is obviously zero since they're the same atom. They would share that pair of electrons completely evenly. When that's the case, you've got a nonpolar molecule. Then you've got the case where you've got, say, something like carbon dioxide. Carbon, double bonded oxygen, double bonded oxygen. Draw our lone pairs. Now here, the oxygen is more electronegative than the carbon, but since we've also got an oxygen on this side, you've got two equal electronegative atoms pulling the electrons towards it. So essentially you've got a tug of war. You've got the negative charge going in that direction and in that direction. So overall there is not an uneven distribution of electrons. They're pulling in opposite directions, so there is no overall difference in which side is positive or negative. So in this case you've got a nonpolar compound with polar bonds in the compound. So the intramolecular bond is polar, but what you'll have is a nonpolar overall compound. So even though the bond within the compound is negative, so even though the bond within the molecule is polar, the overall molecule is nonpolar. What this leads to is two different types of intermolecular forces. And what we're going to call the first one is a dipole interaction. Whenever you have something that is polar, we say that it has a dipole. Di meaning two, pole meaning positive and negative side. So a dipole is going to have a partial positive side and a partial negative side. Whenever that happens, we have what we call a dipole-dipole bonding or dipole interaction. So for example, let's pick something that doesn't contain hydrogen. Let's say you've got carbon monoxide. C triple bonded to an oxygen and C triple bonded to an oxygen. So you've got two carbon monoxide molecules near each other. Now this is a polar bond. That side is going to be partially negative, partially positive. So it's the interaction between the negative side and the positive side. So when you have polar molecules, let's just say in a system, the interactions between those molecules are what we call dipole interactions. And again, that's an intermolecular force. When you have nonpolar compounds, for example, let's say we have our carbon dioxide. Let's Let's draw our lone pairs there. Carbon dioxide. Since we don't have an overall charge, there is no dipole here, so there's no dipole interactions. But what does happen is you've got to remember that these electrons kind of move all around the structure. Every once in a while in this structure, there's going to be more electrons on one side than the other, just out of pure chance. And what happens is you get a very slight negative charge on one side of the molecule, which would make a slight positive charge on the other side of the molecule. Now these charges are very small and they're very temporary. But what will happen is that negative charge then will push electrons in this molecule to one side, giving that a partial positive charge and a partial negative charge. So there's a very slight interaction that takes place when this happens. And again, this is a very temporary and very weak sort of bond. And it happens when you have a system of nonpolar molecules. Okay, so in terms of strength of bonds, typically we say that ionic bonds are the strongest bond. In other words, they have the highest melting point, the highest boiling point. The reason for that is to get something to melt or boil, you need to break apart the interactions between the compounds, or ions in this case. So typically we say that ionic compounds have the strongest bond, even though that's a very, very general statement. There are many, many exceptions to this. Next, we would say covalent bonds have the next highest strength. Right, what we're really concerned with, though, is hydrogen bonding, dipoles, and London dispersions. In terms of intermolecular forces, hydrogen bonds have the strongest bond, dipoles would be next, and then London dispersions would be the weakest bonds. So what this means for us is when you're looking at a compound and you're trying to determine what has the highest boiling point and, say, freezing point. If something undergoes hydrogen bonding and you're comparing it to something that undergoes dipole interactions or London dispersion, the thing that undergoes hydrogen bonding is going to have the highest boiling point because it has the highest intermolecular force. Dipole would be next, and London dispersion would be next from that. So again, when we talk about properties, what we're typically talking about is melting point and boiling point. The thing with the highest intermolecular force, or the strongest bond will have a higher melting point and the higher boiling point. The thing with the weaker bond has the smaller or smallest boiling point and freezing point. Okay, this ends our brief discussion about intermolecular forces. Again, there'll be practice problems at the end of the on the Moodle site, and there are some practice problems on the links following these lessons. So I would do those and then ask your questions on the Moodle site.